So, who's excited about this amazing technology called XML? Some people are. Okay, let's try something different. Who's excited about zero-click attacks on messengers? Or maybe some more people. Okay, well, that's a shame because it's more about the first topic than about the second one. I can understand the lack of excitement in some of you about XML, though, because you see, when XML was young, I was a young computer science student, and I wasn't excited about it back then either. Some people were, though. So, you know, I remember this one guy who was like excited about it and talking about how it's this amazing new technology. And I'm just, you know, I'm standing there, I'm politely nodding my head, but inside I'm thinking, gee, I must have chosen the wrong profession. So fast forward 2 decades later, I'm finally excited about XML for all the wrong reasons. So yeah, XML, you can do stuff with it if you're a security researcher. Anyway, welcome folks to XMPP Stanza Smuggling, or How I Hacked Zoom. I'm Ivan Fratric. I'm with Google Project Zero. I've been doing this security research for a long time now. I stopped counting after 10 years because counting after that just made me feel old. I also wrote some security tools to help others with security research, and we might even see some of them in action in this talk. Right, so let's talk about XMPP. XMPP stands for Extensible Messaging and Presence Protocol, and it's essentially instant messaging protocol based on XML. And when something is built on top of technology that's over 2 decades old, you know it's a good target for security research. So XMPP is a protocol that's used in various applications. It's used in some messengers. It's used in some applications that have a messaging feature, like Zoom, for example, but also in other applications. For example, it's these days quite popular in online games, and also I hear in industrial applications. So even though this talk has Zoom in the name, it's not really only about Zoom. Most of the stuff you hear today is going to be applicable to other targets. However, since Zoom is the most high-impact target that I know that uses XMPP protocol, Zoom is going to be used as an example throughout this presentation, and there is also going to be an exploitation case study later in the talk. So as I said, XMPP is a messaging protocol based on XML. And the way it works is you have XML sent over stream connection. So here you can see an example of how an XMPP stream simplified might look like. So at the start, it starts by opening a stream tag, which would be at like the root level of the XML tree. And then at level 1 of the tree, you have some snippets of XML that are called stanzas. And the stanza is a basic unit of transfer in this XMPP protocol. So here in the slide, you can see examples of 2 stanzas. One is a message stanza, and this is an example of something that's meant to be sent from one client to another. In this case, it's an actual instant message. The second one is the IQ stanza. And unlike the first one, IQ stanza typically isn't sent from one client to another. It's more meant to be exchanged between the client and the server. So these are kind of control messages. And when you see this in security, when you see control messages being sent over the same text-based connection as user-controlled data, then you might be thinking about injection attacks and lack of escaping. And this might work depending on how the service is implemented. However, it's not exactly what we'll be talking about today. Instead, let's examine some other features of this XMPP protocol. So what you can see here is an example of a message stanza from the perspective of the sender and the perspective of the receiver. So on the top, you can see what the sender sends. On the bottom, you can see what the receiver receives. And you can see it's more or less the same. You can see the message highlighted, but you can also see a bunch of XML tags inside this stanza. So one thing I was wondering is, what would happen if I put some other XML tags inside this stanza? And a surprising result, at least to me, was that this custom XML made it all the way through. And I'm not sure how you folks feel about this, but when I saw this, I was like, mind blown. Because I thought, you know, I can do stuff with this. And it turns out you really can. One note here, though, is that any custom XML you put in this way needs to be valid from the perspective of the server, because the server is going to parse this XML, and if the server encounters a parsing error, then it's just going to terminate the connection and not process the stanza further. So speaking about the server, let's take a look at how a typical XMPP infrastructure looks like. We are just going to focus on parts that touch XML directly. Obviously, it's way more complicated than this. But how it works is that a client sends a stanza to the server, which is in XML format. The server needs to parse it, and then the server would do whatever processing it needs to do based on the stanza type. And then if the server decides that this is a stanza that it needs to forward to another client, it's going to serialize it. It's going to convert it from object representation back into text representation. It's going to parse it. It's going to send it over that stream connection to the client, and then the client needs to parse it again. So at this point, let's try to answer the question, what can go wrong here? And the first part of the answer you already saw, which is that you can send custom XML all the way through this pipeline. But by its own, this doesn't give you anything. However, let's combine it with the fact that XML is complicated and XML parsers have quirks. And if you don't know what I mean by quirks, then here's a challenge for you. Find me two XML parsers, two different XML parsers that always, for every input, will result in the same output. And I'm willing to bet that you're going to have a very hard time with that. So at this point, let me introduce what I call XMPP Stanza Smuggling attacks. In theory, it's an attack where a client sends a stanza with some custom XML embedded. The server parses this stanza, sees a single stanza, nothing unusual, sends it to the client, and then the client parses this again, but instead of seeing a single stanza, it sees multiple stanzas. So in a way, we are smuggling stanzas from one client to another through the server, hence the name of the attack. And this is not a single vulnerability. In fact, there can be different vulnerability types that enable this kind of attack. So for example, the first type that I saw was due to differences between XML parsers on the client and the server. However, you can also have bugs that enable this attack that are server only, typically due to interaction between the parser and the serializer. And finally, you can also have bugs that are client only. And once again, this talk is not only about Zoom. So here you can see bugs that affected Zoom, but also you can see bugs that affected other targets. Some of these bugs affected multiple targets. And I can also neither confirm nor deny that there are other bugs not listed in this slide. But as I said, Zoom is going to be used as an example. So it's useful to see how this XMPP infrastructure looks like in Zoom case. So on the client, Zoom uses a library called Glux, which is an XMPP client library, open source. It has its own XML parser. And on the server, Zoom is based on XMPP server called eJabber-D, which is written in Erlang, if you can believe that. eJabber-D has a library called fastXML for handling all of the XML-related stuff. And fastXML uses another library, which is more popular, which is called XPath for XML parsing. At this point, you might be wondering, how the hell does he know what Zoom runs on their servers? Well, whenever I want to know what someone runs on their servers, one thing I like to look at are the job ads. And here you can see conveniently a job ad for a senior XMPP engineer at Zoom, and there is a word that stood out here, and that word is Erlang. And Erlang in combination with XMPP can only mean eJabber-D. So at this point, let's take a look at a few bug examples that enable this stanza smuggling attack. The first example we are going to look at is going to be due to differences between parsers on the client and the server. And this one has to do with UTF-8. And you are probably like, oh no, now he's going to talk about UTF-8. Wasn't XML enough? Well, yes, I am, but only briefly, sorry. So basically, the only thing you need to know for about UTF-8 is captured in this table taken from Wikipedia. And the only thing you need to know for the purpose of this talk is that in UTF-8, you can encode characters using different number of bytes. So some characters you can encode using a single byte, some using 2 bytes, some using 3 bytes, some using 4 bytes. So for example, if you have a byte EB hex, then it could be a start of a 3-byte sequence. And I'm saying could be because if you have a sequence like this, then it's actually an invalid sequence, because while the first byte is a valid start of a 3-byte sequence, the remaining 2 bytes would need to have their highest bit set in order for the sequence to be valid. But let's now take a look at how different XML parsers handle this invalid UTF-8 sequence. XPath parser is going to claim that this is a valid 3-byte character. And the glux parser is going to claim that these are 3 different characters. And the funny thing, besides the fact that these 2 parsers can't agree, is that both of these are wrong. This is an invalid sequence. It should result in a parsing error. So if we take this basic principle and take it one step further, then you can do some fun stuff with it. You can, for example, construct a string that, if parsed with XPath, XPath is going to see a single XML tag. However, if the same string is parsed with glux, glux is going to see 2 tags. And then if you take this and take it further, then it shouldn't be difficult to see intuitively that this can be used to smuggle stanzas. Here you see the payload that I actually used in my Zoom exploit. We're not going to analyze in detail how this works due to in the interest of time. I think it's more important to understand the basic principle from the last slide. However, one thing that I'm going to say is that, again, talk is not only about Zoom. So this exact same vulnerability, besides Zoom, also affected Cisco Jabber, because Cisco Jabber, in combination with Cisco IMN presence, uses the exact same parser pair as Zoom. So this was an example of a vulnerability due to differences between parsers on the client and the server. Now let's take a look at an example of a different vulnerability, a server-only vulnerability. And this one is quite specific to XPath. And to see how it works, we need to take a look at how XPath parser is used inside eJabber-D. And so here in the slide, you can see the relevant initialization code. And the most relevant part here is this last parameter here with the value of \n. Now what this is, it's a separator that is used when XPath returns tag names to the library user, eJabber-D or fastXML in this case. To understand how it works, let's take a look at a couple of examples. So for example, if you have a tag with a namespace attribute, then what you receive from XPath is a namespace and the tag pair concatenated using this separator. And it gets more complicated if the tag also gets if a tag also has a prefix, because in this case, instead of the namespace tag pair, the user receives namespace tag prefix triplet, again concatenated using this separator. Now, as you're probably well aware in security, whenever you are concatenating strings using a separator, you need to pay special attention that the component strings you are concatenating can't contain this separator. So let's see if that's actually the case here. So if you just tried to put a new line character in namespace attribute, it wouldn't work. However, if you numerically encode it, it will work. And what the user receives looks like to the user as namespace tag prefix triplet. However, what the user thinks is a tag name is actually going to be a part of the namespace attribute. And this gets very bad very quickly because there are other characters you can put in the namespace attribute that aren't valid inside the tag name. So for example, you can even construct tag name which contains other tags. And then when this gets serialized, then all characters you put inside the tag name get output as is. And again, it should be intuitively obvious that this can be used to smuggle stanzas. This bug might even be more dangerous than the previous one, because while the previous one required a specific pair of XML parsers, this one affected everyone that used eJabber server, which is a quite popular XMPP server implementation. All right, so now that we've seen some bug examples, let's talk a bit about how you can find such bugs yourselves. And two obvious ways are black box testing and code review. And you might be thinking, well, it makes sense. The UTF-8 issue could have been found by just black box testing, and the separator issue could have been easily spotted by code review. However, if you think that's how I actually found these issues, then I have you fooled, because both of these issues were found using fuzzing. And since fuzzing is something that's more commonly used to find memory corruption issues, let's see how it can be used to find logic bugs like this. So once again, we return to our XML pipeline slide, because this is the thing that we need to fuzz. However, don't think for a second we are going to do any kind of network fuzzing. This would be a very silly and a very wasteful thing to do. Please don't do network fuzzing unless you absolutely have to. Instead, we're just going to take out the libraries that play a role here and put them in a single binary. And then whenever you fuzz for logic bugs, one thing you need to define is what constitutes a bug. And for us, what we are going to consider a bug is going to be a parsing error at the very last stage of this pipeline in XML parser on the client. So here you can see an example taken from the fuzzing harness that I actually used to fuzz this. So what it does is it takes a sample, wraps it into some XML tags, and then feeds it to the server parser and serializer. And if this part errors out, that would mean that the server caught an error. So we just return. We don't consider this a bug, no crash. However, if this part succeeded, then we take the output of the server serializer and feed it into the client parser. And if this part errors out, then that means that there was something on the client that the client wasn't supposed to see that made its way all the way through the server. And so if we get this, we actually cause a crash, and here I just cause a crash by forcing a null pointer dereference. If you find a bug like this, it doesn't necessarily mean it's exploitable for stanza smuggling. However, at least in my case, all of the bugs that I found this way did turn out to be exploitable. For fuzzing this, I used jackalope fuzzer. It's not necessary to use this fuzzer. You can use whatever fuzzer you like. However, jackalope is the fuzzer that I wrote and that I actually use whenever I do any kind of general purpose fuzzing. I think it's pretty good, though I might be slightly biased. However, one thing that is important with regards to selecting a fuzzer is that your fuzzer has coverage feedback. And to see why that's important, consider that when I fuzzed this, my input corpus was pretty bad, and it contained neither numerically encoded character sequences nor special XML attributes like XML and S. All of this was found by the fuzzer on its own using just coverage feedback magic. So at this point, you saw some bugs. You know how to find them, but it might not be obvious what you can do with them. And it was not obvious to me either when I started this research. I had some bugs, but for a while I felt a bit like an underpants. No, you know, I have something, I want to do something with it, but the step in between is kind of vague. So let's see what you can actually do with stanza smuggling. The first thing you can do is message spoofing, meaning you can send a message to another client, and the other client is going to think that this message is from someone who didn't actually send it. This follows from the fact that if you smuggle a message stanza, then all of its attributes, including the sender attribute, would be completely under your control. This is something that you can always do with the stanza smuggling attack. However, it's probably the least interesting thing you can do. The more interesting thing you can try to do is redirect the XMPP connection to another server. And the capability that would give you is to be able to intercept all of the victim's communication. Good news, at least for the attackers, is that XMPP spec already provides a way to do this through see other host error stanza. Unfortunately, though, most of the XMPP implementations that I saw don't implement this part of the spec. The good news, though, is even though they don't implement it as prescribed by the spec, they still implement it, but they implement it in custom ways. Not always, but sometimes. Why they do it this way instead of just following the spec, I have no idea, but it's obvious that they still that XMPP installations, especially larger ones, still find this functionality useful. Another thing you can try is looking at custom XMPP extensions. For example, Zoom client defines over 50 custom Zoom-specific extensions to the XMPP protocol. And then if you find any configuration data that travels over these extensions, then it would, of course, be completely under your control. And one other thing you can try to look for are memory corruption bugs that you otherwise wouldn't be able to reach because they require stanzas that one client can send to another client. So here, for example, you have a quote from Pwn2Own write-up from last year. In their exploit, a feature was used in a stanza that normally one client shouldn't be able to send to another. Now, in this case, it was possible to do due to an issue unrelated to stanza smuggling. However, when you have a stanza smuggling primitive, then you don't need to worry about what one client can send to another. You can send everything you like. So let's now try to put all of that together and use it to hack Zoom. When I started this research, I attempted various approaches for exploiting Zoom, and mostly I was looking at custom XMPP extensions. I found some interesting stuff, but nothing that would really give me a zero-day RCE. The breakthrough, however, came when I noticed that Zoom made custom changes to the glux library, specifically to the handling of the error stanza inside the glux library. Specifically, Zoom added support for a tag called revoke token inside the error stanza, and this revoke token tag supported an attribute called web domain. So naturally, I wondered what would happen if I put my own domain inside this web domain attribute. And what would happen is that I would get an HTTP post request for an endpoint called cluster switch. So at this point, the question becomes, what does this cluster switch endpoint do? And for the purpose of finding that out, I set up a man-in-the-middle proxy in reverse proxy mode, meaning that it proxied requests to the actual Zoom servers. And then when you do this, you are able to observe the response from the server. And what the server response for this endpoint was, it was a really large configuration protobuf. But the part of that protobuf that I found the most interesting was a pretty large list of domain names. And these are domain names that Zoom client uses when connecting to various services on Zoom servers. So for example, there's a domain for web, there's a domain for XMPP, etc. And if you replace all of these, then you would be able to intercept all communication between the Zoom client and the Zoom servers, which is already quite nice. However, what I really wanted was zero-click RCE, as I mentioned, and I had an idea about how to do that, and that was to hijack the auto-update mechanism. In order to do that, what I replaced was the domain that Zoom client uses to connect to the Zoom's web server. So let's recap how the attack looks like so far. It starts by attacker exploiting a stanza smuggling issue and sending a payload with an error stanza with revoke token tag. And when the victim client receives this, it immediately requests the cluster switch endpoint, which the attacker can proxy, but replace the domain used for web. And then eventually, the client is going to request auto-update information using the release notes endpoint. And we can again proxy this, but replace the URLs used to download update components. The way Zoom auto-update works is that Zoom downloads two files. One is called installer.exe, and the other one is called zoom.msi. And even though this one is called .msi, it's actually just a 7-zip archive that contains the actual update files. And since we can replace both of these files, you might be thinking that it's game over. Unfortunately, not quite, because of integrity checking. Specifically, Zoom client checks the signature of installer.exe before running it, and installer.exe checks the hash of zoom.msi before unpacking it. And on the first glance, this looks pretty solid, right? But one thing you can do is a downgrade attack. Specifically, I found that version 4.4 of Zoom installer is on one hand still properly signed by Zoom, but on the other hand, it skips the integrity check on zoom.msi, it just unpacks it. So it actually looks like it's game over at this point. So let's take a look at all of this in action. Sorry. Let me just restart. This is a video demo. It needs to be a video demo because the bugs are patched on the Zoom servers. So even if I had old clients, it wouldn't work. I'm sorry that there is a lot of things going on around here, and text might be a bit difficult to see, but you don't need to see it. I'll explain everything that's going on. But also, if you just want to see better, then feel free to just come closer to the screens in the room. So what we have here is attacker's VM on the bottom left, attacker's proxy on the top left, and the victim VM on the right side of the screen, which is just a clean Windows VM with the most recent version of Zoom at the time installed. The attack starts by the attacker running Zoom client under instrumentation, and this instrumentation allows the attacker to intercept and modify raw XMPP traffic. So here you can see some of that traffic. What happens next is that the attacker sends a very special message, and the instrumentation running in the background replaces this message with the Stanza Smuggling payload. When the victim client receives this message, it immediately requests the cluster switch endpoint, which we proxy, and then from that point on, the victim client continues to use our server instead of the Zoom's web server. What's going to happen next is I'm going to restart the client on the victim machine. The reason for this is that Zoom checks for auto updates about 1 minute after it starts. It might happen at other intervals as well, I didn't check. But even if the attack requires restarting of the victim client, I still consider it zero-click because everybody's going to restart their computer sometimes, at least to install OS updates. And if you don't do that, well, then you have worse problems than Zoom exploit. So right now, we are just waiting for the victim client to check for updates. I'm just going to skip ahead until the point that happens. Or actually, I don't need it. It's going to happen any second now. You should see a request for release notes endpoint. There it goes. And then after that, there is the downloading of those two files that you saw a couple of slides back. So first is the update archive. It's a bit larger, so it takes some time. And the second file is smaller, so it should be done quickly. And then, if you restart the victim client one more time, it should start the auto update process. However, when the auto update finishes, instead of launching the updated version of Zoom, you get something else. Thanks. I should note that calculator is just the means to show that I have RC at this point. In a more realistic scenario, you would actually launch a normal Zoom executable, but you would also launch whatever payload you want in the background. Okay, let's now go back to my slide deck now. Demo we already saw. Okay, so to wrap it up, I think that these Stanza smuggling attacks are pretty underexplored attack surface. I was able to find many different bugs in different targets. And unfortunately, the way XMPP protocol is designed kind of makes it easy to introduce and also to find bugs like this. And the bugs themselves can be pretty dangerous. So the impact can range all the way through relatively benign message spoofing, all the way through intercepting private communication, to, as was just demonstrated, zero-click RCE. And finally, please don't underestimate fuzzing for finding logic bugs. Finally, I'd like to just thank some folks, thanks to who this story has a happy end, I believe. So specifically, Sebastian Pipping of Expat, who was really helpful with getting the Expat issues fixed. Zoom security team, who took all of these issues very seriously and made really comprehensive patches. And finally, my team members, and I thank them for their annoyingly useful comments during the course of this research. Thank you.